So, if we compare between these programming techniques, so this the programming technology, if it is a fuse based programming, then it is not reprogrammable, because once the fuse is blown, so we cannot restore it. So, it is not volatile, like even if you switch off the power, this blown switch will not come back to its original value. So, that is not programmable, not volatile. And the technology that uses is the bipolar technology. Normally it is a TTL type of technology, transistor logic type of technology that is used in the fuse. Then EEPROM. So, EEPROM it is also programmable definitely, but you have to take it out of the circuit, because for reprogramming, so you have to take it out of the circuit and expose it to ultraviolet light, and then only the content will be reset, and then you can program it again. So, that way it is EEPROM is reprogrammable, but it is out of circuit. It is not volatile, because the content will never be lost. The technology that uses is UV CMOS, ultraviolet CMOS technology. Then we have got EEPROM technology, programming technique, and this is programmable, and it is in circuit programmable, because you can just program this, you can apply suitable voltage, and then the PROM content will be modified. So, it is also not volatile, and the technology is electrically erasable CMOS technology. Then this SRAM, so this is also reprogrammable, and it is in circuit reprogrammable. So, that is fine. It is volatile. So, if you switch off, the content will be lost. So, the FPGA chip has to be programmed again, and the technology it uses is the CMOS. And this anti-fuse, so anti-fuse it is not programmable, it is not volatile, and it uses technology which is CMOS plus. CMOS plus that we have said that silicon oxide nitride type of connections. So, this is some advanced masking will be required over and above this normal CMOS fabrication. So, this is the summary of comparison between these programming techniques. Next, we will be looking into this FPGA logic blocks. So, logic blocks are the heart of this FPGA chip. So, they are actually the modules which will be implementing the logic function that we are going to have. So, there are wide variations in the logic block structure of FPGAs available from different vendors, and here actually there are you can find that different FPGA vendors, they have come up with different type of logic block structures, and they vary widely. They vary in the number of inputs and outputs, amount of area consumed, complexity of the logic functions that they can realize, total number of transistors needed, etc. So, that way there is a wide amount of variation. The logic blocks can broadly be classified into two categories. One is called fine grained logic block, another is called coarse grained logic block. So, as the name suggests, so you can understand that when we have got very fine very simple logic block consisting of less number of logic gates in them, so they will give rise to this fine grained logic block. And when we have got this complex logic block, so having individual logic block having more number of functionality implemented within it, so they will be called coarse grained logic block. Now, we will see the trade off between them, and which one is superior, so it is difficult to answer. So, each one have got their own advantage and disadvantage. So, but so the choice is depends on many things, like first of all the availability, then the familiarity of the designer. Like if I am familiar with the Xilinx FPGAs more, so maybe in my future design I will be using Xilinx FPGAs only. So, that way it is like that. So, choice is more determined by availability, familiarity, and in some cases the price also. So, first we look into this fine grained logic blocks. So, this is a logic block from crosspoint. So, this logic block contains a few transistors that can be interconnected via programming. So, for example, so this crosspoint FPGA, so it uses a single transistor pair for each Boolean variable in the logic block. So, this is the thing, like so we have got a p type transistor and an n type transistor. So, that is used for one Boolean variable. So, you have got a chain of such transistors, and you can establish these connections. So, you can do metallization, so that this programming, so that these gate lines, so they can be connected to some inputs. Similarly, this drain and source lines, they can be connected to some they can be connected in some fashion. So, that can happen. So, here is a small example. Suppose we want to realize the function f equal to a b plus c bar. So, you see so from this function you can understand. So, if c is equal to 0, then the function must output a 1. So, if you look into this design, if you see if I put c equal to 0, then what will happen? So, this transistor will be off. So, this transistor will be off because this is n type transistor and I am giving 0 to the gate. So, this will be off, and this upper transistor will be on because this is a p type transistor and I am giving a 0 to the gate. So, this transistor will be on. So, this up arrow means, so it is connected to the supply voltage VCC equal to 5 volts. So, we normally call it VDD in case of CMOS. We in the MOS circuit, so we call it is drain voltage VDD. So, that is maybe equal to 5 volt. So, what will happen? So, since this point is at 5 volt and this transistor is on, so you will get f equal to 5 volt. So, that is equal to logic 1. So, you see if I put c equal to 0, I am getting f equal to 1. Now, this AB part, so AB part is realized by the first part in this section. So, this realizes the product term AB. How? Suppose A equal to 1, suppose A equal to 1 and B equal to 1. So, both of them are equal to 1. Then what will happen? Since A equal to 1, so this transistor is on, this is off because this is n type transistor, and if I give this gate voltage equal to 1, so the transistor will be on. Similarly, this B being equal to on, so this is B being equal to 1, so this transistor is on, this transistor is off. Fine. So, so what will happen? So, this point is grounded. So, you see that this ground potential ground voltage is available here and this ground through this line. So, it will be coming. So, this line is made equal to 0 and you get a 0 voltage here. So, when this 0 comes, so as a result, so this transistor, this is a p transistor with gate value 0. So, this is turned on and this is an n transistor with gate value 0. So, this is turned off. So, you see that this transistor being on, so this voltage, this VDD that we have is available at this point, okay, because this transistor is on. So, this drain and source will be at the same potential. Since the drain is at 5 volt, so this source will also become at 5 volt. So, as a result, this line will be becoming equal to 1 again. Okay. So, on the other hand, if I have this say A equal to say 0, so A equal to 0 and B equal to say 1. So, A is 0, B is 1. So, as a result, this transistor is on, this is off, this is off, and then I have got this transistor as off, this transistor is getting on. So, this is off and this transistor lower transistor is n transistor. So, this is on. Now, since this transistor is on, so you get this 1 value coming here. Okay, so, this is also connected to, this is actually whenever we have got this up arrow means it is connected to VDD. So, it is connected to VDD. So, this is these 2 points potential are same. So, I get a 5 volt here and that 5 volt get transferred to this point. So, when I get 5 volt here, so this transistor will be on and this transistor will be off. As a result, this ground value 0 will be coming to this point and that will be so the ground value will be 0 and this 0 will be communicated to this point, this F. So, in this fashion, so we can have different input combination. As a result, these individual stages of this transistor, so they will be propagating the signal or they will not be propagating the signal. In between, we have got this isolation stage. Okay. So, this isolation stage, so this will be, this is for separating the two product terms. So, this A B and C bar, they are separated by this isolation stage. So, this is this you see that this is an n type transistor and I have connected its gate to ground, the p type transistor I have connected its gate to high. So, as a result both the transistors are off. So, this actually establishes an isolation between this AB term and the C term, and so the logic is transferred from one side to another side by means of these interconnects that we have between these transistors arrays, but otherwise the transistors are not connected to each other by means of the isolation stage. So, that is ensured. So, this way we can have this cross point FPGA. So, they realize this logic functions, and you see the logic block is very simple. So, we have got only 2 transistors per Boolean variable. Okay. So, next we will be looking into a more complex logic block structure, which is from Xilinx, which is Xilinx has got a family of FPGAs. So, this is one of the initial families, I should say. So, today if you look into the advanced families of Xilinx, so they are very complex, we will see some of them. So, this is the XC4000 series from Xilinx FPGA. So, what it has is, this is a coarse grained block, because you will see that the logic function that you can get is quite complex. So, compared to only 2 transistors that we had in cross point FPGA. So, here we have got this type of lookup table. So, lookup table means, so this has got 4 inputs G1, G2, G3, G4. So, it can realize any 4 variable function. So, this lookup table can realize any 4 input function, any 4 input function. Similarly, this lookup table also can realize any 4 input function. So, this so I can if I look to take them separately, then I can realize 2 4 input functions directly from the lookup table. So, number of 4 input Boolean functions that you can have is 2 power 4, that is 2 power 16. So, it is 65536. So, this is the total number of 4 variable functions that we have, that the total number of 4 variable functions that are possible. So, you see this is a huge number of functions that you can realize using this 4 input lookup tables. Plus there is another lookup table after this. So, there the output of these 2 lookup tables are fed, and also this from this C1, this C1, C2, C3, C4 through this selector you can select one of these inputs to come to this lookup table. So, if I take these 3 lookup tables together, then I can realize any 5 input Boolean function, because if I have, so if I have got a 5 input Boolean function f x1, x2, x3, x4, x5. So, we know that by Shannon decomposition, so I can write it as x1 bar into f of x1 equal to 0 plus x1 into f of x1 equal to 1. So, this x1 line can be connected to this C1. Now, this can realize, so this lookup table can be used to realize f x1 bar, and this lookup table can be used to realize f x1, and this selector can be programmed such that it comes here ultimately. So, this lookup table realizes the 3 variable function consisting of the variables x1, f x1 equal to 0 and f x1 equal to 1. So, these 3 functions can be these 3 variable function can be realized by this lookup table. As a result, combining these 3 lookup tables, you can get any 5 input function realized. So, that is very powerful. Okay. So, after the lookup table, after the basic combinational logic function that we can have. So, we see that there are other elements. For example, there is a multiplexer here, and from this multiplexer you can either pass one of these lines through this or you can pass this output of this G, or you can pass the output of this F lookup table, or you can pass this output of this lookup table. So, this is a 4 input multiplexer. So, you can pass any of these 4 inputs to this D flip flop S. Okay. So, this is similarly to this D flip flop. Similarly, for the lower side also we have got another D flip flop, and this you can pass this flip flop values, you can pass this combinational logic into these flip flops, and so as a result the value will be stored. So, as you know that whenever we are trying to realize this finite state machine type of structures, so what we have is we have got some combinational logic, and that combinational logic feeds some flip flops. So, they feed some flip flop for the this next state values. So, this is the structure of a finite state machine. Now, you see if you look into this structure, so it is very much likely that this combinational logic I will be able to realize using these lookup tables, and I have got 2 flip flops. So, these 2 flip flops so these 2 flip flops can be used to do that. So, you see a sizable amount of finite state machine can be realized by a single FPGA logic block of Xilinx. And of course, if there are large number of such logic blocks available. So, if in your design, if there are 1000 in this family XC4000 family. So, if there are 1000 such configurable logic blocks. So, they are called configurable logic block or CLB. Then these 1000 such CLBs, so they will ensure that you have got so there are large number of flip flops in the design in the chip. Okay. So, normally we can use them for realizing any complex finite state machine with large number of states and all. So, that can be done very easily. So, this makes this Xilinx family of FPGAs quite popular, because with this coarse grained logic blocks, so you can put a good amount of logic into individual blocks, and of course, we can connect them with one another. Next, we will be looking into another coarse grained logic block from Actel, which is known as Act1 logic block. So, compared to Xilinx FPGA, so they are not that much that much logic rich, I can say. But it is quite simple. So, we have got 3 multiplexers connected in this fashion. Okay. So, these 3 multiplexers are connected and there is one OR gate. So, these 3 multiplexers and this OR gate, so they can realize some functions. So, these multiplexers can be programmed like say, so the overall logic block has got this 3 plus 3 plus 2, total 8 inputs. So, this overall logic block is of 8 input and 1 output. So, so it of course, it cannot realize all 8 input functions, but if you analyze this particular block, so it can be shown that it can realize up to all 3 input functions. So, up to all 3 input functions can be realized by this logic block. So, it can be proved. Similar for 4 input, so it cannot realize all. So, it is not all, but many of the 4 input functions can be realized. So, this way if you enumerate, then there are around 700 to 800 unique functions that can be realized by this Act1 logic block. So, that is also quite large number. So, because of the advantage that these individual logic blocks are pretty small. So, you can have more number of logic blocks within the FPGA chip, but compared to this Xilinx FPGA, so they are much simpler. So, next we will see how this what are the trade offs between this coarse grained logic block and the fine grained logic block. Whenever we are looking for this coarse grained logic block, a larger logic block can implement more logic within a single block and requires lesser number of logic blocks to realize a given functionality on FPGA. So, individual logic blocks are having more number of functionality that can be implemented there. So, I will require less number of such logic blocks. So, the number of interconnects that will be needed will be less. So, it will require the delay of the design will be low, because the interconnects they contribute significantly towards the delay, and with the increase in the length of the interconnect, the delay increases by the square of that. So, as a result, so if the length of the interconnects are small, then the delay of the design will be less. So, a large logic block can implement more logic function within a single block. So, it requires lesser number of logic blocks to realize a given functionality on FPGA. The other hand, a large logic block consumes more space on FPGA. As I said that, say for example, this Xilinx XC4000 logic block that we have seen. So, this is quite powerful, no doubt. It has got large number of flip flops within it. So, we have got say 1000 logic blocks, and each are having 2 flip flops in them, so 2000 flip flops. So, are we going to use really these 2000 flip flops in our design? So, if you are not using that, then of course, there is a wastage, and there is no way to tell that okay, I will not use these flip flops. So, they will remain whether you use it or not. So, they remain in the FPGA chip. So, so that is there. So, there that is a wastage of space. So, the large logic block consumes more space on FPGA. Now, there is a study that shows that among these lookup tables that we have, so 4 input lookup table they gives best result in terms of logic synthesized and area consumed. So, if you make a trade off plot, so some early researches they have shown that that this 4 input is the ideal value. 3 input if you make, so that is also not good. 5 input also we cannot, they are not very much useful, but these 4 inputs are better. A higher granularity level results in lesser delay between system input and output. This point I have already said that we have got this interconnect length will be small. So, as a result the delay will be less. With the increase of the granularity level, average fan out increases and number of switches also increases as each block has more pins. So, one output may be one output of a logic block may be going to 10 different places. So, as a result the fan out will be high. So, that way again that is another point. So, if fan out is high, so we have to put some buffer in between. So, as a result the overall logic requirement will also go up, and length of the wires increases with increase in the size of the logic block. So, if the logic block is so if you look into this FPGA chip, as we have shown you that if these are the logic blocks and say this is another row of logic blocks. So, we have got interconnects running between them. So, if these logic block sizes are small are large, then naturally this interconnect length is also going to be large. So, that is why we have got and that is another problem. So, if you have got larger sized logic block, then the length of the wires will also increase. So, that way it may be better that we go for smaller size logic block or final logic blocks. So, the overall FPGA design flow is like this. So, no FPGA based designs are done manually. So, first of all it goes through a design entry phase. In the design entry phase, it can be either by a schematic entry or it may be a behavioral entry. So, schematic entry means, so you draw your circuit in terms of AND or NAND NOR gates and say flip flops and all. So, you draw your design in terms of that. Normally FPGA vendors they provide you some logic libraries. So, we take the elements from that logic library and draw our schematic in terms of that. Then so other possibility is that you describe your design in some language like VHDL or Verilog type of language, and then from there you go through a synthesis stage. So, that will convert your description into a circuit. So, whatever you do, whether you directly enter the schematic of your design. So, normally for smaller designs and for more if we are looking for optimized design. So, we go for this schematic based strategy, so that the overall control is in the hand of the designer, or we can have this behavioral entry. So, behavioral entry is normally there when we have got the entries from the more complex systems. So, we want to it is difficult to draw the circuit directly. So, go for this behavioral design. So, whatever and the design synthesis, so these are the CAD tools. So, that will convert this description onto this implementation. So, after we have got this implementation, so implementation is by means of this logic elements that the library supports and the interconnections that we do. So, we do some timing verification and all. So, we will come to that, and then it goes to device programming. So, once this design has been implemented, so this device programming, so it generates a control program for the FPGA, and that control program is used for say if it is an SRAM based FPGA. So, it will be used for it will be downloaded onto the FPGA chip for functioning. If it is antifuse or this one time programmable FPGAs, then these device programs, so they will be used to burn the appropriate fuses or antifuses, and that way this connection the FPGA will become functional. So, this is the design process. So, design, whenever we are doing the design, digital design, the verification also comes into question. So, if you are having this behavioral specification, or so normally we can do a simulation of it. So, we can put some sort of test vectors and see like whether it is giving me proper result or not, that is via behavioral simulation. Similarly, for the design synthesis also, so we can go via some simulation and do that. And for the once the design has been implemented, so you can go for functional simulation. So, to see whether functionally it is giving correct result or not, you can do a timing analysis. So, now maybe in your design entry, so you have put output of one block to connect it to the input of another block, but while you have done the implementation, so these two blocks are placed far away on the FPGA chip and they are going through a number of interconnect stages for doing the for getting the connection between the 2 points. So, as a result, the delay of that wire will be more. So, that will be captured in the timing analysis phase. So, in the timing analysis, it will find out whether there is any timing violations, etc., and then it will be giving all the wire delays, and those wire delays will be back annotated into the original design. So, that is the stage of back annotation. So, the delay values are put onto the design and then we do another timing simulation. So, after timing simulation, so if we are satisfied with the timing simulation, then only this device programming is done, and once the control program has been loaded onto the FPGA device, so we can go for in circuit verification. So, this in circuit verification, so they will be it can verify if there is any problem in the actual running of the system or not. Normally, if your design is through this timing simulation, so we can be sure that the design will work in the final implementation as well. If you look into the modern FPGAs, so in addition to the basic blocks such as the logic blocks, IO blocks and interconnects, modern FPGAs have additional units that help in the design process to make it simpler. The two major components that we have that we do not have in FPGA, what FPGA, these logic blocks and all, one is embedded memory, another is block for arithmetic calculation. So, the various calculations, multiplication is the most widely used one, because FPGAs may be used for some signal processing type of applications, so multiplication will be very important, and most of the modern FPGAs, they contain embedded logic blocks for multiplication and memories to hold the data. So, DSP functional digital signal processing functionalities are highly facilitated by the availability of this multiplication and multiplier and memory. In many applications, FPGAs need to communicate with microprocessors. So, the FPGA chip that needs to communicate with some outside chip, and many FPGA vendors, they have embedded some soft processor codes within FPGAs. So, these processor codes are there, so you can very easily use the communication mechanism supported by those soft codes of the processors that we have that is embedded into the FPGAs. For example, the Xilinx, they have got PowerPC embedded onto this FPGA chip. So, that way we can have this microprocessor, it can establish a communication between the microprocessor and the FPGA. So, Xilinx Vertex 6 and Vertex 7 series of FPGAs. So, just to have a brief idea, the CLB of Vertex 6 can be configured as 6 input LUTs or 2 5 input LUTs. So, these are the advancement. From 4 input it comes to 5 and 6 input. So, LUT can be used for 64-bit RAM or 32-bit RAM. So, that is so that way it gives you to store some RAM space there. So, Vertex 6 FPGA has 156 to 1024 dual port block RAMs, each storing 36 kilobits. So, that a huge amount of RAM space is provided. Dedicated full custom low power DSP slices are there, so that can do digital signal processing calculations. It has got 17 channel 10-bit ADC, 8 to 72 Gbps transceiver. So, 10-bit ADC, 17 different analog signals can be fed into this 10-bit ADC for doing the analog to digital conversion, and this transceiver is there for communication. Vertex 7 is 3D IC, so 3-dimensional integrated circuit. So, again it has got much higher capabilities.